We need to be able to predict molecular geometries. The first thing is to obtain or draw the Lewis structure for the molecule. Next, determine the total number of electron groups around the central atom. Figure out how many bonding and lone pairs you have. And then this is such stupid advice from the book. Refer to table 11.1. Okay, that's not going to work because there will be questions like this on exams and I'm not giving you the table. You look at the table and it looks really, really complicated, but it's actually not. Find out how many total electron groups. Think about what that many balloons would do, right? You know, if you want, you know, I command you to go out and buy some balloons and play with them, right? It can be really helpful. How do those balloons arrange themselves? And then look at the lone pairs, and those guys are invisible. With just a little bit of attention, you can remember those names of all those molecular geometries because they are related to the shapes. Yeah?
Sorry, when I said the balloons that many, so are they, the electrons, the lone pairs, are they just like sitting in an orbital so they're just kind of pop, like the balloon like an orbital, or?
Well, they will have an orbital.
I know the orbitals kind of look like balloon shaped before.
So this is more like what the lone pair would look like compared to the bonding pairs.
Okay.
So the lone pair is just going to take up a lot more space.
Okay.
Yeah. And we really don't want to think too much about what shape those orbitals are.
Okay.
At least not yet.
Okay. But those are like kind of still floating around in one of the orbitals. Like.
Yeah, the lone pair will be in an orbital
Okay.
on the atom. And when we get to valence bond theory, we'll talk about how that works. Predict the molecular geometry and bond angle of Cl and O. Let's start with the Lewis structure. 5 electrons from nitrogen, 7 from chlorine, 6 from oxygen. I believe that's 18. And we've got bonds here. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18. We don't have enough to give oxygen an octet. So we're going to take a pair from the nitrogen and shift it in here and make it a bonding pair. So, we got a double bond with the oxygen, got a lone pair on the nitrogen, got lone pairs on the chlorine and on the oxygen, but those don't matter for figuring out the shape. We look at the central atom. How many electron groups? 3. A single bond, a lone group, lone pair, and a double bond. Each of these is a group. So 3 groups. What do 3 balloons do? They make a triangle, right? So they're going to make a trigonal planar structure. One of these has a double bond. So the molecular geometry, oh, wait a minute. There's a lone pair. So I made balloons, and now I need to make one invisible. So that one's invisible. That's the lone pair.
Is that considered bent?
Yeah. So this will be considered bent. And what do we know about this angle? What if it was a perfect triangle? 120? Be 120? Is this going to be less than 120 or greater than 120?
Exactly. Oh no, less than.
Less than. Because this guy over here is very repulsive, and so those guys are going to squish together a little bit.
Distance, which would be greater, the distance between the lone pairs and the single, or the distance between the lone pairs and the double?
That's a good question, but I don't know that it is relevant, really, at all. Because that question is really, well, is this slightly off-center here or not? And even in terms of the molecular shape, it doesn't matter. I'm not sure how you would measure that, actually. We can measure bond angles, but yeah, I don't think we can measure angles of a lone pair with a bond. Yeah?
If you're talking about the electron geometry, it's going to be linear.
For that one, the electron geometry would be trigonal planar, because we have a single bond and a double bond, and then we've got a lone pair. So that's 3 groups.
So electron geometry, we think about a lone pair too?
Yeah. So when you find the number of electron groups and you think about, well, what would the balloons do? That's your electron geometry. And then you make the lone groups invisible, and that's your molecular geometry.
Got it.
Let's try I3 minus. Well, we don't have much choice but just to put these i's in a line. We've got 3 times 7 plus 1 for the charge, right? So 22. Got 1, 2, 3, 4, 6, 8, 10, 12, 14, 16, 18, 20. We got another electron pair. I'm going to put that on the central atom. The central atom is big enough to expand its octet. And then I'll put brackets around this because it's an ion, and put the charge on the outside. Move those guys over a little bit because they're kind of crowded. How many electron groups on that central atom?
2, 3, 4, 5.
5. 3 lone pairs, 2 double bonds. Yeah.
I thought if it was a -1 charge, we just add 1 electron, or we add a pair?
No, we added 1 electron. Because there would have been 21, and I added 1. Yeah. It's just when I was counting by 2s, I had 2 left. Okay, so 5 groups, what's the electron geometry? The little girl, the tutu, but the tutu only has 3 balloons. Trigonal bipyramid. So 5 groups. Trigonal bipyramid. And then we've got lone pairs. Three lone pairs. We're going to cut off her head and her feet? No. We're going to cut off her skirt. Right? We can cut off the 3 balloons of her skirt. Let me try to draw this. Okay, so these are the axial ones, and these are the equatorial. So the lone pairs are going to go where there's more room. They're going to go in the equatorial positions. The cutting off the head thing just came up just like within the last hour. So that's, and I'm really liking it, actually. So which ones are going to be invisible? Is it going to be her head and her feet in one of these? No, we're going to make the skirt invisible. chop off the skirt, we're not going to chop off her head. So if I make those invisible, let me see what's a good way to do that. What's the shape?
Linear.
Linear. You look at this Lewis structure and you're like, well, that's going to be complicated. No, actually, this should be linear. So this is linear. Any questions? This is going to take some practice. But what I like about this is it's a lot more visual than a lot of the stuff we've done. I mean, think about superposition of electrons being waves and particles at the same time and all these different shapes overlapping with each other. And now we've just got like nice balloons that don't get into each other. I like this. We need to be able to communicate when we're drawing molecules that they are not flat. And so we typically use just a line to mean that this is in the plane of the screen. And a hatched wedge means it's going behind. It's like a dotted line, right? You can't see it because the screen's in the way, so it's dotted. And this one's jumping out at you. So if I'm trying to make like methane that's a tetrahedron, what you want to do is you want to put as many of those atoms in a plane as you can. And then I've got one that's going to be jumping out and one that's going to be going behind. And you will need to draw these things on worksheet 11. I want to be able to tell that you tried. Okay? So if you draw this, I don't care how you label the angles. If you draw that, that is wrong because that is flat. You didn't even try. So this is not okay. What if it comes out like this? Well, it's not very good, but I can tell you tried. All right, so that's good enough. Okay, you're asking about larger molecules. Larger molecules have more than one interior atom, and what we're going to do is we're going to look at the geometry at each of the interior atoms. So this is the amino acid glycine, and there are 4 interior atoms. So we can look at the geometry around nitrogen. Well, there are 4 groups, tetrahedral, 1 lone pair. So that's trigonal pyramid. And here this carbon has 4 groups, no lone pairs, so that's tetrahedral. Here, 3 groups, no lone pairs, trigonal planar. Here, 4 groups, tetrahedral, but 2 lone pairs, so it's bent. And then this is what a model might look like. So let's do this one, and then we'll call it a day. So we really need the Lewis structure, and this is not the Lewis structure, so I'm going to fix it a little bit. Because we need to see if we have lone pairs on central atoms, and we need to see all the bonds. So this carbon on the end, and there will be a question like this on the exam for chapter 11. This carbon on the end, what is the molecular geometry around that carbon? How many groups does it have? 4. What do 4 balloons do? Tetrahedron. And there's no lone pairs, so nothing becomes invisible, and so we're just done. How about this other carbon? How many groups? 3. No lone pairs? What do 3 balloons do?
Yeah, like a triangle.
They make a flat triangle. Trigonal planar. And this oxygen. 4 electron groups, so tetrahedron. 2 of them are invisible. Bent. Okay. Now it says make a sketch of the molecule. I won't make you do this. So I'm just going to start on the end with that oxygen, and this is the hydrogen, and I guess I'm going this way. It's bent, and so here's the carbon, and here's the double bond to the other oxygen, and this is going to the other carbon, and then this guy's tetrahedral. Yeah. Okay, use your imagination. Okay, what's the molecular geometry around nitrogen in this compound? Again, you gotta have the Lewis structure. Well, if you do the Lewis structure, that's what you get. 4 groups, tetrahedral. 1 is invisible.
Oh, and then
A pyramid?
Trigonal pyramid.